So now we will discuss what lenses are and what happens to light that is passing through lenses. Why is this important to us? We use many lenses in our day-to-day life, or many instruments that have lenses are used in day-to-day life. You have seen all these, or at least you know what they are. Now here the first picture, it's a hand lens. You would have seen people using hand lenses to read very tiny letters. Sometimes with age, sometimes even when we are young also, if the letters are very, very tiny, or if there are some symbols or carvings on an object or an ornament, you like to look at it in an enlarged manner. So you want to see it bigger. Then what do is we take a hand lens and observe through it. And sometimes when there are people, because of their eyesight problem, they can't read tiny letters, then also they use hand lens. The same way, if you want to observe, say, the wings of an insect, in order to learn about insects, if you want to look at the structure of a small insect or the wings, then also you can use a hand lens to observe it. So therefore, we give another name to this hand lens. What do we call it? We call it as a simple microscope. Why is it simple? Because it uses only one lens, and that is one biconvex lens. We will be discussing the types of lenses, but you are familiar with it already. It is a biconvex lens. So what happens when you use more than one lenses to magnify the object? Then that becomes a microscope. You know this is a compound light microscope. Why do we call it compound? Because there are more than one lenses. This is the lens which is known as the eyepiece, through which you look at the or you observe the slide or the specimen. And here there are many objectives, different lenses with different powers that are near the stage. So there are two lenses, the eyepiece and the objective. So there the magnification happens due to the two lenses. That is why we call it as a compound light microscope. So either way, in a simple microscope, a hand lens, or a compound microscope, that is the light microscope, we use lenses to magnify objects. So the smaller objects or tissues or parts of cells, but the cell structures cannot be observed very clearly using a compound microscope, that you know, but you can look at the basic structure. So to observe all that, we use microscopes that have lenses. The same way, the spectacles. Here you can see spectacles. Again, spectacles use different types of lenses, and you all know why we use spectacles. What is the reason? There are some people who have the short sight defect, and there are some people with long sight defect in the eye. So to correct these defects, you can either use a convex lens or a concave lens. So we use spectacles with different types of lenses, different thicknesses of lenses, in order to rectify or correct the short sight or long sight defect. So spectacles are another instrument or thing that uses lenses. Then there are another two instruments. You know what this is? It is a telescope. Why do we use a telescope for? We use telescopes to observe stars and the objects that are there in outer space. They are very, very far away from us, so we can observe them closely and the image will be magnified. The same way, we use a binocular to observe a scenery or something that is far away from us. So there also you can see a distance or far away object closer to you, and also the image will be magnified. But there is a difference, or there are more than one differences. Here there is only one place through which you can observe, and also the image will be inverted. You know the meaning of inverted images. But here the binoculars are very comfortable. Why? You can look through both of your eyes, so it's like normally looking at an object, and also the image that forms is an upright image. And we have discussed about binoculars as well as microscopes and camera. There is one common factor there. What is it? The total internal reflection by prisms. That is also related to optics, that is used in microscopes, binoculars and cameras. So like this, if you look at many different instruments and many different instances in our day-to-day life, we use lenses. So if we see what a lens is an optical device. It is an optical device with curved surfaces. So it can be curved outwards, it can be curved inwards, and one can be a flat surface and the other surface can be curved. So either way, it will have curved surfaces, and it can be made of glass, plastic or any other transparent material. That is the important thing. Those days, it was mostly made up of glass. But with glass, the problem is if it falls, it can break easily, it can crack easily, and also it's heavier compared to plastic lenses. Plastic lenses are very light, and also if it falls down, it won't break that easily. So because of that, nowadays, the lens made up of plastic is more commonly used, even for spectacles. Those days it was made up of glass, now it's mostly made up of plastic. But the important thing is it has to be a transparent material. What is a transparent material? A material that allows light to go through. A lens alters the path of light rays that pass through it by refraction. So I told you all this is refraction by lenses. Images on the retina of our eye are formed by a lens. You are familiar with the structure of your eye, and you all know there is a biconvex lens. The curvature of that lens can change so that you can look at close by objects as well as far away objects, and the image forms on the retina. What type of an image is that? A diminished, that is smaller than the object, and it is inverted, and also it's a real image. That is why it forms on the retina. And how do we get the information? From the retina, information is taken to the brain through the optical nerve, and there the information is obtained in the correct manner. So you can see how a complicated process takes place within our eye. But there are lenses. So we basically use the lenses every day because in our eyes also we have lenses. So therefore it's important for us to know how lenses refract light and how images are formed by lenses. So we have discussed all these optical instruments. Many lenses are made of glass, but now plastic is increasingly used for making lenses. I told you all why. Any transparent material can be used to make lenses. So you can even use water. Sometimes even liquids such as water are used to make lenses. So like that, lenses can be made using many different types of liquids as well. But only important thing is they need to be transparent material. So with that, if we look at the types of lenses. Now these lenses again can be made up of glass or it can be made from plastic. Now I said there are curved surfaces. Now if you look at this, it has two curved surfaces. And the curvature, it's curved outwards. You can remember, students, we use two types of mirrors, convex mirror and concave mirror. Convex mirror, the reflective surface was curved outwards. So this is similar to that, but here there are two curved surfaces. So we write it as bi. Bi means two. Biconvex lens. So what is the difference here? Here one is curved outward, so it's convex, but the other side is flat like the plane mirror. So here we call it plano-convex lens. This is plano-convex lens. Then we have the other type. Here both the curved surfaces are curved inwards and there are two surfaces. So you can guess the name, biconcave lens. So this is biconcave lens. So what is this? One side is flat like the plane mirror and the other side is curved inwards. So it has to be a plano-concave lens. So this is plano-concave lens. So we have a biconvex lens, plano-convex lens, biconcave lens and a plano-concave lens. The way they refract light, all of these refract light will vary. But for us, we will be using the biconvex lens and the biconcave lens. So if I move on to convex lenses. The two surfaces of a convex lens can be considered as parts of two imaginary spherical surfaces. We discuss this with mirrors as well. Mirrors were part of hypothetical spheres. But here the lenses have two surfaces. Since it's a convex lens, the surfaces are curved outwards and those two surfaces are parts of two imaginary spherical surfaces. So if we look at that, imaginary spherical surfaces, the shapes, okay. Now let's say this is one sphere, there is another sphere like this. We'll try to make it almost the same size. Okay, here you can see this is one sphere and this is another sphere. Now let's say I will label the spheres. This can be sphere 1, or let's say I'll label it as sphere A and this as sphere B. Now the two surfaces that overlap and intersect, if you look at the shape of the spheres, you can see this shape. It is a biconvex lens. And this center, I can label it as C1, center of sphere A, and this is C2, that is center of sphere B. So if I write those two here, C1, center of sphere A, and C2, center of sphere B. Now if I use a line to connect the two centers, now let's say I have a line going through the two centers of the two spheres. Here this is one center and this is the other center. Now these two fall in one line, and that line is known as the principal axis. Principal axis. And any ray that is going along this principal axis, this is perpendicular to the lens. If we draw a line like this, these two are perpendicular to each other. This is the center of the lens, and here the light ray, if it goes along the principal axis, that will be perpendicular to the lens. And this point, that is the center of this lens, is known as the optical center. So this point is known as the optical center of the lens. So students, this is how we get a biconvex or convex lens. Two spheres, imaginary spheres, and when they intersect like this, you get the biconvex lens, and these are the two centers of the two spheres, and the line going through the two centers, or line connecting the two centers, and the middle point of the lens or the center point of the lens is known as the principal axis, and that is perpendicular to the plane of the lens, that is this line, and where that intersection is, that is this point, is known as the optical center. So these are the parts of the biconvex lens that you need to understand. So here if we look at how light rays travel through the optical center, so I told you all at this point we have the optical center. How do we get the optical center? That is the intersection between the principal axis and the plane of the lens. At the points where the principal axis intersects with the surfaces of the lens. Surfaces is what I said as plane of the lens. So the principal axis is perpendicular to the surfaces. Therefore, a light ray that enters the lens along the principal axis will leave the lens without bending. So here it will not bend. The midpoint between the two surfaces of the lens is called the optical center of the lens. It is possible to show that any light ray that travels through the optical center passes through the lens without any bending. So we can show that here. So to show that, we will have to draw a line going through the center of the lens, and also this is the surface of the lens. So here you can see they intersect each other. So this point is the optical center. So if the light ray is going through this along the principal axis, it doesn't bend, it goes straight. Why? This angle is 90 degrees. If we take any other ray that is going to go through the optical center. So let's say we take a ray going like this. Now here also it's perpendicular to this surface. So therefore, that is also going through the optical center and that doesn't bend. It goes in the same path. Say another ray going in a different direction like this. So that also goes in the same path. It does not bend. So here again that is the optical center. So all the rays that travel through the optical center, they go without bending or they travel in the same path. It doesn't have to be only in this direction. Even if the light comes this way, that also passes through the optical center without bending. If it comes from there to here, the same thing. If it goes in this direction from here to there, it does not bend. So any light ray that passes through the optical center is perpendicular to the surface of the lens. So therefore, it doesn't bend. So that is the ray that is going through the optical center. So going through light rays traveling through the optical center. So this is how light rays that travel through the optical center travel without bending. Now we will see what will happen to a parallel beam of light when it travels through the convex lens. To observe that, we will discuss an activity. Activity focusing of light with a convex lens. So for that, these are the materials we need. We need a biconvex lens, and also we need white paper. It doesn't have to be really white paper, but it's easier to observe the light on a white paper more clearly. So if we have these two, we need a source of light. Normally, we get parallel beam of light from the sun. Why? The sun is a very far away object. So if we get the sunlight, rays from the sunlight, it will be a parallel beam. Otherwise, we can use parallel beam of laser light as well. If there is an instance where you cannot get the sunlight, then you can use a parallel beam of laser. That is also if you have it. It's a very simple activity. I will go through the steps of the activity. So first what we are going to do is when there is bright sunlight. So again, to get a parallel beam, hold a convex lens to sunlight and place a white paper in front. So we keep a white paper in front, adjust the distance between the paper and the lens until you get a very small patch of light on the paper. That is very important. So what happens? The rays are coming parallelly. So it's a large beam of light. But those light beams come onto one point on the paper. So it's a small patch of light on the paper. And at this point, because the sun is very far from us, we can consider all the rays of light coming from the sun to be parallel. So here what we do is, after we get that patch, we measure the distance between the lens and the patch. So once we do that, we measure the distance. So here I will include another step. Measure the distance between the lens and paper when a small patch of light is obtained. What will happen if you hold it like that? Now say we are doing the activity with sunlight. Maybe you had tried this before, or you can try it even after this. Get a biconvex lens, focus the bright sunlight onto a piece of paper, adjust the lens so that the patch of light becomes a very tiny dot. For this activity, we need to measure the distance between the patch of light, that is the paper, and the lens, that is the length between the lens and the paper. But if you can direct the light onto the paper for a long time, what will happen? The paper will start burning. Why? We are directing a lot of heat rays in addition to the light rays, and all of them get focused onto one point. That is why we get a very small patch of light, and due to that amount of heat energy, the paper starts burning. You can try that and see. If we don't have enough sunlight, as I told you all before, as an alternate method, we can use parallel beams of laser light in order to observe that all these lights focus onto one point or converge onto one point. So in this activity, I will not be using the sunlight. I am going to use the laser light in order to observe how light rays are focused onto one point. So now it is a simple activity. Let us do it in the lab. So here students, I have parallel rays going through the convex lens. You can see the middle ray going through the principal axis, the other rays going parallel to it, and you can observe that they focus on one point. To make this more clear to you all, I will push the lens and the laser beam to a side so that you can observe it more clearly. Now here you can see that all the rays, the incident rays are all parallel, but they all converge on one point. That is the focal point of the biconvex lens. Okay students, so if we have used the sunlight, the parallel rays will be like this, like shown in the picture. And those rays, when they pass through the convex lens, they will all converge towards one point. You know that this is a parallel beam of light, this is a converging beam of light. And at this point, there will be a small patch of light on the paper. And the distance between the lens and the paper will be the focal length. Why? Here, all the light rays are focused onto one point. Onto one point. And that point is known as the focal point or the focus. So that is what we call as focal point or focus. So when light rays focus onto the paper, the length or the distance between the lens and the paper where the rays get converged onto is known as the focal length. So here, as I told you all, this is a parallel beam of light. Beam. And this is a converging beam. So the light rays are converged onto one point, and that point is known as the focal point or the focus. So that is what we are going to observe here. So from that activity, what can we conclude? We can conclude, or we can actually measure the focal length of this biconvex lens. So that will be the conclusion of the activity. The focal length of the lens can be measured. That is, if we did the activity using sunlight. But what was the activity I did? I used the laser light, a parallel beam of laser light. So what were you able to observe? You were able to observe that the light traveling through the biconvex lens focus onto one point, and that is the focal point or focus. So you were able to observe the focusing of light by a biconvex lens, and you saw what a focus or a focal point is. So with that, we will move on to the next one. Sun is very far from us. We can consider all rays of light coming from the sun to be parallel. In this activity, you will observe that when parallel light from the sun passes through the lens, all of the rays are focused onto a single point. So here we had the biconvex lens, and the parallel rays that came, they were focused onto one single point, and this point is known as the focus or focal point, and these were parallel beams, and these were the converged beam of light. And what is this length? This is the focal length. So that is what we were able to observe from that activity. So it can be either sunlight or any other parallel beam of light. You can observe how they focus on a point. So with that, I will move on to the next one. The way the rays parallel to the principal axis are refracted by a convex lens. This is what we observed during the activity. You know that they all focus onto one point, or they converge onto one point. How does this happen? You also know that lenses refract light. Why? If you look at this lens, this is made up of glass. So this is glass. And what is on either side of the lens? That is air. So this can be glass, or this can be any plastic material, but you know this is more denser than the air around it. So if we look at the way the rays fall onto the lens. Now here you can see these are parallel rays. Now we will consider this first ray. When that is incident on the surface, here you can see there is a normal. That is, at the point of incidence perpendicular to the surface of the lens, there is a normal. And then because it's going from air to glass, the light ray bends towards the normal. Here you can see it should have gone this way, but it bends towards the normal. And then when it falls on the second surface, this is glass, this is air again. Then what happens? It bends away from the normal. Why there? Glass is the denser medium, air is the rarer medium. So here you can see it bends away from the normal. So because of that, they bend twice, that is they refract and go through this point. The same way here, the incident ray, it refracts at this point, again refracts at the second interface, like we discussed with the glass cube. Incident ray, refracted ray and the emergent ray. So here the two emergent rays, they go through one point of the principal axis, and that point is known as the focal point or focus. So therefore they all go through the same point, they get focused onto one point. And the length between the lens and the focal point, that is denoted by simple f, and that is known as the focal length. So this is focal point or focus, and f is the focal length. So we use a capital letter to denote focal point and a simple f to denote the focal length. Now if I come back to the text. When such a ray enters the lens, so here parallel ray, they enter a denser medium from a rarer medium. So denser medium is glass, rarer medium is air. Then the ray bends towards the normal to the surface. When this ray leaves the lens, it enters a rarer medium from a denser medium. So here it is from the lens to air again. Therefore, it bends away from the normal. So both are visible in the diagram. In both cases, the light ray bends towards the principal axis. This is important. It bends towards the principal axis, here and here. Here and here, both ways it's towards the principal axis. It is possible to show that all rays that enter the lens parallel to the principal axis after bending as discussed above travel through a single point on the principal axis. So they travel through a single point. This point is called the focus or the focal point. That is what we discussed there. Focal or the focus, focal point or focus of the lens. The distance from the optical center of the lens to the focal point is called the focal length. So here this is the optical center C. From that point to F is the focal length. So these are the parts of a biconvex lens and how rays focus onto the focal point. So because this happens, different rays are refracted in different ways. We already saw how a light ray coming along the principal axis goes in the same path without undergoing any bending. Now here we discuss the ray that is coming parallel to the principal axis, bending through the focal point. So those are two types of rays. Light can enter from either side of the lens. That is also important. It is possible to identify two focal points for a lens. So there are two focal points for a lens. I will start with the principal axis. Then if we draw a line perpendicular to that, This is going to be the biconvex lens, and this is the optical center. That is C. So the rays that come this way can bend through the focal point on the other side of the lens. So here we will have a focal point F. The same way, rays coming from this side, they can bend from the other side of the lens. So they will focus on this side of the lens. So here there will be another focal point. We can denote it as F dash. And the length, this and this will be equal. So if we take this length from the optical center to F as simple F, and here from this point to the optical center as F dash, will be equal to F dash. So both the focal points will be at equal distances from the optical center. So this is one focus and this is the other focus. So the ray that is coming parallel from this side will go through that focal point. Rays coming parallelly from the other side will go through this focal point. So either way, there are two focal points for a lens. But these points have the same distance to the optical center of the lens. That is this. Same distance to the optical center of the lens. Normally, when ray diagrams are drawn, the focal point is denoted as F, that is this, and the focal length is denoted by simple F. That is this. So, since there are two, we can use it as F and F dash or F1 and F2 to denote that they are on either side. So, that is what we do here. So, then we can see how light rays are refracted by the biconvex lens. Images formed by convex lens. So, now students, you already know that convex lenses refract light. And how do they refract? If the ray is coming along the principal axis, it goes along the principal axis without bending. But if the rays are coming parallel, they bend and focus onto the focal point. So either way, when rays are refracted, they form different types of images. To understand how these images are formed, we should first know the focal length of the lens. So, we will be doing this first activity to measure the focal length of a biconvex lens. So, here you can see this is a biconvex lens. So, we need a biconvex lens, and we need A4 paper or white paper or a screen. We can either hold a paper, we can use a screen, and I have told you all before also, if we can't find a screen, we can even use the wall as our screen. So here this is an activity to find the or measure the focal length of the biconvex lens. So a simple one where you need to have a object or a scenery that is far away from us. So something that is out of the window. If you are inside the lab or the classroom, you can focus the image of an object, maybe a tree, that is outside the window. So what we do is we focus the image of that object onto this screen or A4 paper or the wall, and we adjust the lens so as to get the very sharp image. And when you get the image, you will see it will be smaller than the object. We call it the diminished image, and it will be inverted. It will be upside down. So, it will be an inverted image. And because you can get it on the screen, it's going to be a real image. So, once you get that diminished, inverted, real image, which is very sharp, we hold the lens in place and we measure the distance between the screen and the lens. That will be the focal length of the lens. The reason is the rays that are coming from the faraway object, that is the objects that are outside the window, they are parallel rays. So, these parallel rays focus on the focal point. So, the image forms on the focal point. So, therefore, by measuring the distance between the lens and the screen, we can get the focal length. So, that is the method of this activity. Open the window of a room, hold a convex lens, turn towards the window on the opposite side of the lens. So, here object is on one side of the lens, the screen is on the other side. So, on the opposite side of the lens, hold a screen or a white paper and adjust the distance between the lens and the screen until a clear image. This is what I said as a sharp image. A clear image of the scene outside the window is formed on the screen. Measure the distance between the lens and the screen when you get a very clear upside down image on the screen. So, that is the activity. Let us do this activity in the lab. So, now I am going to do an activity to find the focal length of a biconvex lens. So, for that I have a screen already prepared for us so that we can get the image, and you know, if the image falls on the screen, it's going to be a real image. And here, to find the focal length, we have to get the image of an object that is far away from the lens. So, what I have done is, I have kept the screen so that we can focus an object that is outside the window. So, here first I will place the biconvex lens. You can see it here, students. Both sides are curved outwards. So, it is a biconvex lens. I will place it in the holder, and then now I will try to focus the image onto the screen. I have to move it so that we get a very clear image. Now we have a clear image. Just to make sure that's the most clear one. So, here I have the clear image. So, we have the clear image of the plant that is outside the window. And here on this stand, I have points marked here and here so that it's easy for us to measure the length between the mirror and the screen. So, now what I am going to do is I will measure first. It is about 8.8. So, here you can see this is the marked point. So, when I hold the ruler, you can see it is about 8.8 centimeters between the screen and the biconvex lens. So, that is the focal length of this biconvex lens. Okay, students. So, you saw how the image formed on the screen. We were able to get the image of a plant, the inverted, diminished, real image of the plant on the screen. So, this is how it happened. This is the window, the plant was outside. The rays that come from the plant, because it's a faraway object, are parallel rays. That is important. Parallel rays. And parallel rays focus onto the focal point. So through the biconvex lens, we get the image onto the screen here. That is the clear inverted image of the object outside the window, and you can see the window as well. Here you can see it is inverted, diminished and real image. So this is the observation. If we write down the observation here, real, diminished, that is smaller than the object, and also it's inverted. Image, object, inverted image is obtained. And we can measure the length. So that will be the focal length. So the conclusion of the activity, image of a faraway object forms on the focus. So therefore, we can measure the focal length. So we can measure the focal length. So focal length can be measured. How do we do that? By measuring this distance. This is the focal length. Distance between the lens and the screen. So that is the activity where we measure or determine the focal length of the lens. So here, using this lens, we can observe the different type of images formed by the biconvex lens. And then, as you know, we can draw the ray diagrams for all these images. To do that, first we will see how different types of rays are refracted by the biconvex lens. Drawing ray diagrams for images formed by convex lenses. The size, nature and position of the images formed by convex lenses depend on the distance between the lens and the object. So here the size will vary and the nature. Now we saw if it is a faraway object and the rays are coming parallel from it, it is a real image, it's an inverted image and it is a diminished image, that is smaller than the object. So size and nature, and also it formed on the focal point, that is the position of the image. But when you change the distance between the lens and the object, so here it depends on the distance between the lens and the object. These properties, the position, the size and the nature of the image will change. In drawing ray diagrams for images formed by convex lenses, it's convenient to use specific rays. So that is what we are going to do now. We will see how different types of rays are refracted by the convex lens. So here we have the first type. So a light ray passing through the optical axis. So you all know what that is. It is the principal axis, and normally when we draw a line like that perpendicular to the principal axis, that is the surface of the two mirrors, and the point where it intersects is known as the optical center. So here basically we are going to look at the ray that is going through the optical center. So to observe, we have already done this, but to observe how this happens, we first need to draw the principal axis that is going to go through the center of the lens, and here we have to draw another line. This is the line perpendicular. So here it will be the optical center. The C. And the ray is going to come along this, the optical axis or the principal axis. So that is going to pass through the optical center, and therefore it doesn't bend. So it will travel along the principal axis. We already saw there can be rays coming from different angles also, but still they will go through the optical center, then they will not bend. So we can show another ray that comes along the optical axis and goes without bending. So if there is a ray like that also, that will go without bending. So that is a light ray passing through the optical axis that passes through without any bending. So the same way, if there is another ray coming this way, that also passes without bending. So that is one type of ray. So students, you know how the ray that is coming through the optical center goes along the same path. Let us observe this type of optical ray now. So students, when I send a ray through the principal axis, you can see it's going straight along the principal axis. But when I turn it at an angle, can you all see? What can you see? Although it's coming parallel to the principal axis, you can see that the ray is changing path. It is getting refracted. The same way, if I push it to the other side of the principal axis, although the ray is coming parallel, incident ray, but the refracted ray is at an angle. But if I place it in the middle, you can see that the ray is going straight along the principal axis. So that is the optical center. Through the optical center, if we send a ray at an angle, now here again see the ray is getting bent, that is refracted. But if I send it at an angle through the optical center, you can see it going in a straight line. Same way from the other side also, if I send it through the center at an angle, that is the optical center, the incident ray and the refracted ray are same. But if I turn the angle, you can see the ray is getting bent. So this point through which the rays travel without changing the path through a biconvex lens is known as the optical center. So again here you can see the ray traveling without changing path. So that is through the optical center. So you saw that the rays that are coming along the optical axis do not bend and they travel along the same path. Now we will move on to the next type of rays. A ray that enters a lens parallel to the principal axis. So here to draw that ray, first we need to draw the principal axis. So here I have the principal axis. Then what do we need to do? We need to use a broken line to show the refracting surface of the lens. So, we will be refracting the ray on this line. What is the next step? We need to mark the focal points, and it has to be on either side of the lens. So, here there is going to be one focal point at the 5 centimeter mark, and on this side also at the 5 centimeter mark, and you have to write it as F. You can also mark the 2F points, but here I'll only mark the focal points. So then the ray coming parallel to the principal axis. So here if we take a ray coming parallel to the principal axis, it will come up to this point, and then it has to refract. When it refracts, it will refract through the focal point. A ray coming parallel to the principal axis refracts through the focal point. So this is the ray. And here we need to show the direction of the ray so that you know what is the incident ray and what is the refracted ray. So a ray coming parallel to the principal axis enters the lens and gets refracted through the focal point. With that, I will move on to the next one. A light ray that passes through the focal point on one side of the lens. So this is going to be the opposite of the previous ray. So here again we need to have the principal axis. So I will draw the principal axis here. Then again we need to mark the focal points. So I have, before I mark the focal points, we need to draw the center of the lens. So I need to mark the focal points here and here. So this is a focal point, that is the other focal point. So how is the ray coming? The ray is coming through the focal point. A light ray that passes through the focal point. So if we draw the ray there, let's say I will take a ray that is passing through the focal point. So here again a ray coming this way and passing through the focal point. It will fall on the lens, and from there it has to refract, and that refraction will be parallel to the principal axis. So a ray that is coming through the focal point will refract parallel to the principal axis. So that is the refracted ray. A ray coming through the focal point refracts parallel to the principal axis. It goes towards the other side. So if a ray comes from this side, it will refract parallel to the principal axis on this side. And like you know, there can be a ray coming at this angle. Then it will go along this way, parallel to the principal axis. Because the lens can allow light to pass through and refraction takes place, you know that we can have the rays coming from either side of the lens. So that is how the different rays are refracted by the biconvex lens. So with that, I will move on to the first one. When the object is between the lens and its focal point. So now we are going to draw a ray diagram. To do that, you all need a sharp pencil and also the ruler, so that you will get the correct position for the image. So where do we start? You all know this is a biconvex lens. We have to have the principal axis. So we will start off by drawing the principal axis. So here I will draw the principal axis going across the biconvex lens. Then what do we need to do? We need to draw a broken line for this lens, and it's always better if it goes above and below the lens as well, so that we can reflect the light, the rays on that. Now say if we bring the ray here, a parallel ray, it touches the lens at this point. Then if we refract it, we will be refracting at a certain angle. But if it is at a different point, or if a student draws the refracted ray starting from a different point, then the image will be at a wrong position. So if we draw this line, we can always refract the rays on that line. Then we will get the correct diagram. So now we have to mark the focal point and the 2F position. And you all know the focus and the 2F points are there on both sides of the lens. Why? Light can go from either this side or it can come from that side. So I will mark the points again here also. For convenience, I am using the focal length as 5 centimeters. So here, okay. So point for 2F, F, the F on the other side, and the 2F position. So we have F, F dash, and this side also F and F dash. So this is the focal length from optical center, that is C. This is the optical center C. Between C and F is the focal length. The same way between this C and F is the focal length. So now we have to draw the position of the object. Object is between the lens and its focal point. So here students, you can have the object on this side and on this side. Either way you will get the same diagram. Only thing, the way the incident ray falls on the lens and how it refracts, the direction will change. So I will draw the object on this side between the lens and its focal point. So here I will draw the object somewhere here. That is the object. So we will mark it as O, so that you know which is the object and what is the image. Right. Then we will need to draw the rays. We don't have to draw rays starting from the bottom of the object. Why? Because it is on the principal axis, and any ray that is going along the principal axis will go through in its path. It will not bend. So therefore, the image of the bottom of the object will form on the principal axis. So what do? We consider rays, and that also how many rays? We need to have at least 2 rays. 2 rays coming from the top of the object. So I will take a ray that is parallel to the principal axis. So here the ray that is parallel to the principal axis, we will bring it up to this point. This is what I said. We can refract it from there. Then we need to refract that ray through the focal point. The ray coming from the object parallel to the principal axis refracts through the focal point. refracts through the focal point. Okay. Right. So now I have the position. It will go through the focal point. So that is the first ray. That is the ray that comes parallel to the principal axis, goes through the focal point. Then I will draw the second type of ray, the ray that comes through the optical center. What happens to that? It travels in the same path. That also doesn't bend. So here the ray that is coming through the optical center. So it starts from here and goes through the optical center without undergoing any bending. So that is the second ray. Now if you look at the two rays, can they meet on this side? No. You can see they are going away from each other. So there's no chance the two rays will meet. So obviously they have to meet behind the object or on this side of the lens. So to make them cross each other or intersect each other, what do we do now? We need to extrapolate the rays. You know the meaning of extrapolating the rays. We use broken lines and we make the ray a little bit more longer, so that they will meet at a certain point. Going to extrapolate this ray, and the same way we have to extrapolate the other ray as well. So the two rays meet at a point somewhere there. Then if we draw the image, it will be from this point to here. That is going to be the image. You can see, students, the image is behind the object. It is larger than the object, so we call it the enlarged image, and it's of the same direction, so it's an upright or erect image. Enlarged, erect or upright, and also when it is behind the object, then we cannot get it on the screen. So it is a virtual image. So when the object is between F and the lens, the image will be upright, enlarged and virtual. And also the position is between F and 2F distance. So those are the properties of this image. This is how we observe larger letters when we use a hand lens. You have seen we hold the hand lens a little closer to the book. So you see the letters larger. So that is because the letters of the book or the book is between the focal point and the lens. So you see an enlarged, erect, virtual image. So now we will write down the characteristics of the image. It is a virtual image, enlarged, that is larger than object, and also it is upright. Sometimes we call it erect image. The same size, and it's formed between f and 2f distance. Forms between f and 2f distance behind the object. So that is how we see this image. You can see the image there, and that is the ray diagram. Now I will move on to the next type of ray diagram, when the object is on the focal point. So now we are moving the object away from the lens. Initially it was between the lens and the focal point. Now we are moving it away from the lens. It's on the focal point. So again, to draw the ray diagram, we need to have the principal axis. Then we have the line for the lens. So that is the optical center C. Then we need to mark the focal points. On either side, the focal points, and also this will be 2F, the focal point, then again the focal point on the other side, 2F distance here. So this is how we will have the different points. We'll mark this as F dash, F, F, and F dash. So now we need to have the object on focal point. So it can be either this F or that F. Now previously I drew the object on this side of the lens. So for uniformity, I will draw the object on this side itself. So now we have the object here, we have the object there, and also I will write it as O, so that you know it is the object. Here, because we have both focus or focal points on either side, the image can, earlier we saw that the image formed on this side, and there are possibilities where the image forms on the other side of the lens. So to identify which is the image and the object, we use these letters. So I'll start with a ray that is parallel to the principal axis. Parallel to the principal axis. So it comes to this point. Then how does it refract? It goes through the focal point. This side or this side. It has to come to the other side. So it will refract and go through the focal point. On the other side of the lens. So here again I have the refracted ray going through the focal point. Right. We have to mark the direction of the rays. The ray coming parallel goes through the focal point. Then I will take another ray coming through the optical center. So here a ray coming through the optical center that will go through like this. How does this refract? It won't refract. Why? Because it is coming perpendicular to the surface of the lens. So therefore there will be no bending. It will go in the same path, the straight line. So that is the second ray. Now that we have the two rays, what can you see? The distance between the two rays are the same. So on this side, they will not meet. Even if we extrapolate the rays using broken lines. Here also I will extrapolate the rays. And this ray also can be extrapolated. You can see they are going parallelly. They do not meet at any point. So because the object is on F, the refracted rays travel parallelly. Therefore, they can only meet at infinity. Then the image can form at infinity. So the image that forms at infinity will be an inverted image and very much larger than the object. So an enlarged object that is inverted and it will form at infinity. So here we cannot see the image, only the object is there. So if we write down the characteristics of the image. Forms at infinity. And here it will be enlarged, that is very large image, and inverted. That is if the rays meet at infinity. So that is the second type of image formed by convex lenses. Now we will move on to the next type of image. When the object is between the focal length and twice the focal length. So here again you can see we are moving the object away from the lens. So where do we start? We have to draw the principal axis. And I am sure you all are familiar with drawing the ray diagrams now. You can try it on your own first. So I will draw a very long line to show the principal axis. Then what do? We have to have the line to note the lens. So that is a broken line. You can also use a straight line, but here I am using a broken line to indicate the lens. So that is the length. Then what is this point? This is the optical center C. Then what do? We need to mark the distances. What are the distances? We need to have the 2F distance, that is at 2F distance at 10 centimeters, F at 5, Again on this side, f at 5 centimeter mark, and the 2f distance at the 10 centimeter mark. So those are the points that we need to have. This is f dash, f, and on this side f and f dash. So where is the object? Object is between the focal length and twice the focal length. The focal length is from C to F. What is twice the focal length? That is up to this point. So the object has to be between F and F dash. So again, I will draw the object here. This is that's the object. Now we need to draw the rays. First I will draw the ray that is coming parallel to the principal axis, starting from the top of the object. It has to come and bend at that point. It will refract and go through the focal point. You all already know that. So now if we draw the ray that is going through the focal point. This is the refracted ray. Then we have the ray that is coming from the top of the object and going through C. So here I will start from the top of the object. Here you can see they meet at this point. So that is going to be the place where the image forms. So from here to here, but we started the ray from the top of the object. So the top of the image has to be here where the two rays intersect. And then we have to mark it as image I, and also I have to show the direction for the rays. The ray coming parallel to the principal axis goes through the focal point. The ray coming through the optical center goes along that same path. So it goes straight like that without bending. What can you say about the image? You can see it is beyond 2f distance on the other side of the lens, and also it's upside down, so it is an inverted image, and you can get it on the screen. Why? You can hold the screen on this side, so you will get the image on the screen. So it is a real image. Look at the size. Now this is this much and the image is large. So it is an enlarged or larger than the object image. So those are the properties of the image formed when the object is between f and 2f distance. So it is a real image. It's enlarged, that is larger than the object. And it is inverted, upside down or inverted image. And where does it form? On the other side of the lens beyond 2f distance. Beyond 2f distance. So those are the properties of the image formed by a biconvex lens when the object is between f and twice the focal length distance. Now we will move on to the next type of image. I am sure you were able to identify and write down the properties of this image and you have understood how to draw the ray diagrams here. I will move on to the next one. When the object distance is equal to twice the focal length. So here again we have to start off by drawing the principal axis. It's beyond twice the focal length. I will draw the principal axis. Then we need to have the ruler. Before I mark the focal point and the 2F point, what do I need to do? I have to draw the line to indicate the lens. So to do that, I need to use a broken line, or as I said before, you can also use a straight line. That is also okay. So what is this point? It is the optical center. Then from there, if we mark the 2 points, the focal point here, the 2F is here, and on this side also we have the focal point and the 2F distance. So now I have to mark all the points. This is F dash, F, that's the optical center C here, again F and F dash. Where do we have the object? When the object distance is equal to twice the focal length. So this is the focal length, that is the twice the focal length. So it's going to be on F dash. So we have the object here. So I have the object here. Now what do? We need to draw a ray that goes parallel to the principal axis. So a ray that is coming parallel to the principal axis. So I start from here. It will come and refract from the lens. How does it refract? It goes through the focal point. It will go through the focal point. So here I can draw the ray because I can draw straight lines. Right, it goes through the focal point. Then we have a ray coming through the optical center. A ray going through the optical center. A ray that will go through the optical center. That will not bend. It will go straight through the optical center. Then you can see the two rays intersect at twice the focal length at this point. So here we will have the image from here to here. That is going to be the image. image. So the object was on twice the focal length distance. Image also forms at twice the focal length distance. That is at f dash. If you measure the height of the image, you will see they are of the same height. And this is inverted, and also you can get it on the screen. How? You can have the screen on this side, object is on that side, you hold the lens in the middle. So you can get it on the screen. So it's a real image, it's inverted, and it is the same size as the object, and it forms on twice the focal length distance. So those are the properties of this image. So it's a real image, inverted, then forms on twice the focal length and also same size as the object. So now students, we are drawing the ray diagram for biconvex lens. Don't confuse, but just think of this. We drew ray diagrams for mirrors. Can you remember the concave mirror? When we place the object at C, that is center of curvature, there also you get an inverted image, real image, same size as the object, and also that also forms on C. So can you all see a relationship? The biconvex lens is similar, not the same, because here it's refraction. The image can form on either side of the lens. In a mirror, that is reflection, because there is only one reflective surface. But you can just compare the concave mirror and the convex lens. They do form similar types of images. If you can compare and understand, it will be easy for you to remember what type of images are formed by these different lenses and mirrors. So this is the image formed when the object is on twice the focal length distance. There is something missing in the ray diagram. Can you all identify what that is? We have to show the direction of the rays. So here this ray is coming from the object, and here it refracts, here it just goes in the same path. So always remember, when you draw the ray diagram, check it again to see whether everything has been done correctly. So now that you have understood this ray diagram, we will move on to the next type of ray diagram. When the object distance is greater than twice the focal length. So now we are moving the object away from twice the focal length. Object distance is greater than twice the focal length. So again, we start the ray diagram by drawing the principal axis. Principal axis. Then I will draw the broken line for the lens so that it's easy to refract the rays. What do we do next? We mark the F and 2F distances. we have the right. So I have to mark the F dash, F, optical center C, again F and F dash. So now we have the object beyond the 2F length or twice the focal length. So the object will be somewhere here. Object is here. And we have to write it as O or object. Either you can denote it as O or you can write it as object. Then the ray that is going to come parallel to the principal axis, starting from the top of the object, coming parallel to the principal axis, will refract and go through the focal point. So it has to go through the focal point after refracting at the lens. So that will go through the focal point. Then we will take a ray that is going through the optical center. A ray that has to go through the optical center. So here you can see starts from the top of the object and it goes through the optical center. So here is where the two rays intersect. Then if we draw the image, goes from here to there. So that is the image. What can you see here? Again it is inverted, that is an upside down image. You can see this is smaller than the object. Object is larger, this is smaller. Is it a real image? Yes. Why? It can be obtained on the screen. You can place the screen on this side, you can get it on the screen. So it's real, it's inverted and it's smaller than the object, so that means it's diminished. And it is formed between F and 2F distance. The focal length and twice the focal length distance. So those are the properties of the image form. Again here I have to show the direction of the rays. The ray that comes parallel to the principal axis refracts through the focal point. A ray that comes along the optical center goes without bending, and where they meet we get the image. So now I will write down the properties or characteristics of the image. This is a real image. then inverted image, diminished image, that is smaller than the object and also it is formed between focal length and twice the focal length. So, forms between focal length and twice the focal length. So, those are the characteristics of this image. So, students, now we have drawn many ray diagrams. We started with the object being placed between the optical center and the focal point, or the lens and the focal point. Then there was a certain type of image. Then we placed it on focal point, then distance between focal length and twice the focal length, then on twice the focal length distance, and now we drew a ray diagram where the object is beyond twice the focal length distance or greater than the twice the focal length distance. And you saw when we change the position of the object, the characteristics of the image and where the image forms change. Try to remember all the ray diagrams. When it was between C and F, the image formed behind the object itself. Then we brought it to F, the image forms at infinity. Between F and 2F distance, then the image formed on this side. Then we brought it to 2F distance or twice the focal length distance. Then the image formed on twice the focal length distance. Then what happened? We moved the object further away. The image comes closer to the lens. So, you all can understand the relationship between the distance of the object and the distance of the image. With that, you all know all the characteristics of the images form. So, now we will summarize the different characteristics of the images formed by the biconvex lens. The following table shows how images are formed by a biconvex lens. So, here we have the object distance, then the position of the image, whether it's a real image or virtual image. Real means you can get it on the screen. Virtual, you cannot get it on the screen. Upright and inverted, upright image, it's the same direction as the object. Inverted is its opposite. And the size of the image. It can be larger, that is enlarged, the same size, or it can be smaller than the object, that is a diminished image. So, now if we look at the first position of the object, less than focal length. This is the first ray diagram that we drew. And you got the image where it was greater than the object distance and it was on the same side as the object behind the object. So, greater than object distance on the same side as the object. All the others form on the other side of the lens. Was it real or virtual? It is a virtual image. Upright or inverted? It was upright. And the size of the image, what was that? It was larger than the object. Larger than the object. How do we call it? Enlarged image. Then when we kept the object on focal length, what happened to it? It formed at infinity. So, if the rays meet at infinity, I said it will be very large and also it is an inverted image. But since we did not see the image, we are not going to write the properties there. Then the next one, greater than focal length and less than twice the focal length. So now we are taking the object away from the lens. Where did the image form? Greater than twice the focal length on the opposite side. Earlier it was infinity. Now it is beyond twice the focal length and it's on the opposite side. So the image is now becoming closer to the lens. We are taking the object away from the lens. Image is coming closer to the lens. What was the nature? Was it real or virtual? It is real. Upright or inverted? It's inverted. How about the size? It is still larger than the object. So, larger than the object. So, again we can call it as an enlarged image. So, here so far you can see the size of the image is larger than the object. Now, we will move on to the rest of the images. The next point, where did we have the object? It was on twice the focal length. So, where did the image form? That was also on twice the focal length, but on the other side of the lens. Twice the focal length on opposite side. Was it real or virtual? It is real. You can get it on the screen. Upright or inverted? Inverted. What was the size of the image? The same size as the object. Same size as object. You can even write it as same size. Then the next one, we kept the object at a distance greater than twice the focal length. We kept it away from twice the focal length, a distance greater than twice the focal length. Where did the image form? It was between twice the focal length and focal length. Greater than the focal length and less than twice the focal length. Here also on opposite side. What was the nature of the image? It was a real image. And it was inverted. What happened to the size? When the object goes far away from the lens, the size of the image becomes small. It was smaller than the object. So, we call it the diminished image. Now, we didn't draw a ray diagram for this. The object is at infinity. Then the image will form at focal point on the opposite side. So here we have the object at infinity. What type of rays come from infinity? They are going to be parallel rays. Let me show you how we can draw that ray diagram. We will use a principal axis. I will use a line for the biconvex lens. So just to show that it is a biconvex lens, I have the lens drawn here, and then we have to mark the focus or the focal point. I will mark the focal point here and the focal point there. Now let's say the object is at infinity, very far away from the lens. How do the rays come? They come parallel. So if we take a ray coming parallelly, so the ray that is coming towards the focal point, how will that refract? Let's say it's coming towards the focal point. So that is one ray. If I draw that ray from a distance, it's coming like that. When it touches this point, it will refract parallel to the principal axis. It will refract parallel to the principal axis. So here that will be the refracted ray. And this is F. This is also F. I need to have twice the focal length as well. I didn't mark it before. And here we'll have twice the focal length. So that's going to be F dash. Another ray coming along F dash. That is going to be parallel to this. But what is coming along the optical center? That is C here. That is also parallel to this. So I will draw a ray that is parallel to this, but is coming through the optical center. So a ray coming parallel to the ray, parallel to this ray, and it is coming through the optical center. Here you can see where they meet. The ray that is coming parallel. So these are parallel rays from infinity. Where does the image form? It is going to form at this point. So you can see the rays that are coming parallelly. One comes through the optical center it goes without bending. Another one coming through the focal point, it refracts parallel to the principal axis and they meet at the point where the F is. So, there the image forms on focal point. So, here object is at infinity distance. What are the properties of this image? It's inverted, it's smaller than the object, so it's diminished, and also you can get it on a screen. So, that is a real image. So, I am sure students, you can draw a ray diagram like this. Always remember the rays that are coming parallel. They are coming from a very far away object. That is why we normally consider an object outside the window, far away from the mirror or the lens, or it is coming from infinite distance. So, that will be the image form. So, if I write down the properties. Infinite distance at focal point on the opposite side, it's going to be a real image and it is inverted and it is diminished. So, here you can see students. Earlier we had the object greater than twice the focal length. It was somewhere here. Still it was a real inverted image. Where did we get the image? It was between F and 2F distance. Then it was also smaller than the object. When you take the object a little bit more far away, you will see that the image comes closer or moves towards F. Earlier it was greater than focal length and less than twice the focal length between the 2 points. But if it was somewhere here, when you move the object a little far away, image will move closer. You move the object further, image will move even more closer. So, when the object is very far away or at infinity, the image will form on F. And also you will be able to see the size decreasing. It is a diminished image, smaller than the object, and still it will become smaller and smaller. So, that is how the biconvex lens forms the different types of images. I am sure by now you know to draw all the ray diagrams relevant to the images formed by biconvex lens. And you have understood all the different characteristics of the images formed. And you can see a relationship between the position of the object and the nature of the image. Now we will do an activity to understand or to observe what these images are. Observe the images formed by a biconvex lens. So, the materials required are a biconvex lens, then we have a screen. It can be a screen or it can be a white paper. White paper. And we need a candle, a lighted candle. Lighted candle. That will be the object. So, you're familiar with this type of activities. What do you think we have to do? We will look at the procedure. So, first we place the biconvex lens on a stand so that it's easy to move it around or just to keep it in one place. Either way, it's always easy to use a stand. place a lighted candle in front of a convex lens. So, one side you have the candle, then you have the convex lens. Place a screen on the other side of the lens. So, here we have the screen here. Then we have the lens, and on the other side we have the candle flame. That is going to be the object. So, you know the lens allows light to go through and it refracts. So, we have the object on one side, screen on the other side. Place the lighted candle at a distance greater than twice the focal length. So, we keep the lighted candle greater than twice the focal length. So, if the focal length of the lens is, say, we'll say 10 centimeters. Twice the focal length is going to be 20 centimeters. So, we will place the object, say, at 30 centimeter length from the lens. So, place the lighted candle at a distance greater than twice the focal length from the lens. Observe the image formed on the screen. So, again, you know, we can't just have the screen at one point. We will need to move the screen a little bit so that we get a very sharp image. Then you can observe the properties. Where does the image form? When the object is greater than twice the focal length distance, it forms between twice the focal length distance and focal length on the other side of the lens. So, we have to adjust the screen between those 2 points. Then what do we do? Move the lighted candle towards the lens and place it at different distances from the lens and observe the images formed. So, here we are going to move the candle, that is the object. We will have it on twice the focal length distance, then between focal length and twice the focal length distance, we can have it on focal length distance or on the focus, then between the lens and the focal length. Then you can observe what type of images are formed. You already know the characteristics of the image. So, it will be easy for you all to identify and hold the screen in the correct place. So, when you have the object at focal length distance, that is focal point, will you get the image on the screen? No. Why? It will form at infinity. The same way, when the object is between the lens and the focal point, you know where the image forms and you know whether you can get it on the screen or not. So, accordingly, we will do the activity. So, again, this is something similar to what we have done before. Let us do the activity to observe the different types of images formed by a biconvex lens. So, now we are going to observe the images formed by a biconvex lens. Now, for that, I have the screen here, the lens, and I have placed the candle very close to the lens. That is between the lens and the focal point. Can you all see an image on the screen? No, we can't see a clear image even if I bring the screen closer or take it away, still I don't see a clear image. So, that means when the object is between the lens and the focal point, you cannot get the image on the screen. Now, I will move it around. Now, you can see, students, I have kept the candle very much closer to the lens. So, how do you see the image? It is larger than the object, so it's an enlarged image and it is in the same direction. So, that means it's an upright enlarged image. Since we can't get it on the screen, it's a virtual image. So, when the object is between the lens and the focal point, we get an image that is upright, enlarged and virtual. So, after that, if I move it a little away, when the object is at the focal point, the image will form at infinity. Then also we can't observe the image. So now I will keep it somewhere far away from the focal point. Then you can see there is an image forming on the screen there. And when I move it away, you can see the image becoming smaller, and also you can observe that it is inverted upside down. And since we can get it on the screen, it is a real image. So when the object is away, when it is between f and 2f, you get the image that is diminished, real and inverted. And when I move it a little bit more backwards, when it is exactly on 2f, then of course you will be able to see the image as the same size but inverted, and it is a real image because you can get it on the screen. So when I move the candle away from 2f, then you can see the image becoming smaller. It is inverted but it is real. So if I take it further away, you can see it's even more smaller, but still it is inverted and it is real. So those are the types of images formed by a biconvex lens. Okay, students. So you saw the different types of images formed by the biconvex lens. What did we do? We changed the position of the object. The distance between the lens and the object was changed. The object was the lighted candle, and you were able to see the different types of images. So those are the observations. Now if we take the first position, here is the object distance, less than focal length. When it was less than focal length, where did you see the image? It was behind the object on the same side. It was enlarged, erect, and it was virtual. So those were the properties. Here less than focal length. It was upright, enlarged, virtual, and on the same side. Here, since I have to write down all the properties, I am writing everything in a shortened form. But you know the meaning of all these characteristics. Then it was on focal length. Where did the image form? It forms at infinity. So here, image forms at infinity. When it was greater than focal length and less than twice the focal length, what was the nature of the image? It was on the other side of the lens. It was greater than the object size, so that is, it was an enlarged image, it was inverted, and it was real. So here it was real, enlarged, inverted, and on the other side. We have already written down the characteristics of all the images before also in the table. And now during the activity, you were able to observe them clearly. Then twice the focal length. Where did the image form? It formed on twice the focal length. Again, it was real, same size, same size, and that was also inverted and on twice, or I will write it as 2f distance. So that was the property of this image. Then we placed it greater than twice the focal length. Then what happened to the image? The image moved a little closer to the lens. So here that was also real, but what was the size? It was diminished, inverted, and it was between f and 2f distance. Focal length and twice the focal length difference. Then we had the object at infinity. Where did the image form? On the focal point. That was also inverted. You were able to get it on the screen, so it was real, and it was smaller in size, diminished. So here you can see, students, the nature of the image or the characteristics of the image depends on the position of the object. So what happens when it is far closer to the lens? You can see it's an enlarged image, but it is virtual. So that is the only instance a biconvex lens forms a virtual image, and that is also enlarged. But all the other images are real. So here that is the only instance where a virtual image is formed. Then when it is on focal length, image forms at infinity. When it is greater than focal length and less than twice the focal length, again it's a real, enlarged, inverted image forms on the other side. And that is also away from twice the focal length. Then when we have it on twice the focal length, real, same size, inverted, and the image forms on twice the focal length. When it is greater than twice the focal length, it's real, diminished, inverted, and forms between f and 2f distance. And when you take it further away from the lens, the object, the image comes closer to the lens. And finally, when we have the object at infinity, it forms on focal point, and it is inverted, real, and a diminished image. So from all these observations, what can you conclude? We can say that the image formed by convex lenses depends on the position of the object. So that will be the conclusion. The characteristics of the image formed by a convex lens depends on the position of the object. And also, depending on the position, the characteristics change. It can change from virtual to real, from enlarged to same size to diminished, inverted to upright. So like that, the properties or the characteristics of the image will change depending on the position of the object. So that is the conclusion that we can get from this activity. So with that, students, I am sure you are very clear about the nature of the images formed by a biconvex lens, and you know how to draw ray diagrams for the images formed. So now we will move on to the next topic, where we discuss the principle of reversibility of light. So principle of reversibility of light is this. We have different optical instruments like a plane mirror, a prism, a biconvex lens and another plane mirror. What happens here is we send or pass a beam of light onto this plane mirror. It undergoes reflection. Here you can say it's undergoing reflection. Then through the prism, it undergoes refraction. Again through the biconvex lens, it is refraction. And finally, it gets reflected by the plane mirror. So it can undergo a series of reflection and refraction processes, but finally it comes back in the same path. That concept is known as principle of reversibility of light. If the direction of the light ray is reversed, so here you can see direction of the light ray. This was the forward direction and it is coming back in the same path. It will follow exactly the same path backwards, and this is called the principle of reversibility of light. So it will follow the exactly same path. So here we have a plane mirror. You all know the symbols. So what happens here? If we draw the normal line there, it gets reflected. So that is reflection of light. So here it reflects. Then it falls on the surface of the prism. It refracts. So this is the prism. Then we have the biconvex lens, and there also its refraction. And here again there is reflection. That is also a plane mirror. So here you can see when the light falls on the plane mirror, what is this angle? That is a 90 degrees angle. So that means light is incident perpendicular to the surface of the plane mirror. So that reflects back in the same path. So again here you can see the light travels back in the same path. That is exactly the same path. So therefore we call it the principle of reversibility of light. So this is the concept of principle of reversibility of light. So you all need to have an understanding as to what happens to the light. It goes in the forward direction, undergoes refractions and reflections, and again it comes back in the exact same path. So here students, you can see this is the laser beam. I am going to generate the laser from there. The mirror, plane mirror is set here. You can see the right angle prism kept and the biconvex lens, and again we have another plane mirror there. So here the light ray that is coming and getting reflected by the plane mirror will go through the prism. It will get refracted. Again it will be refracted by the biconvex lens and it will be reflected by the plane mirror here. So it will travel back in the same path from where it came. Now we will observe that. So students, you can observe the ray coming from the laser pointer being reflected by the first plane mirror, going through the prism, then getting refracted by the biconvex lens, and finally being reflected by the plane mirror again. So it is turned back in its path. Just to confirm to you all that the ray has been sent back in its path, if I move this mirror, you can see reflected ray going in a different path. If I move it more towards this side, again you can see the reflected ray. But when I adjust it to the correct position, you can see that it is only one ray that is going back in the same path. So with that, we have come to the end of discussion on convex lenses.